Pick up a thermometer and watch the silver liquid inside move with every degree. That's mercury, the only metal that stays liquid at room temperature. For over a century, American mines produced thousands of tons of this strange metal, extracting it from bright red rock buried deep underground. The process started with cinnabar ore mined from shafts hundreds of feet deep, heated in massive furnaces until mercury vapor rose into condensing chambers, then collected as pure liquid metal and sealed in iron flasks. This is how America turned red stone into liquid silver, before the toxic reality shut it all down. Mercury mining in the United States peaked between 1850 and 1970, with operations scattered across California, Nevada, and Texas. New Almaden in California became the largest mercury mine in North America, operating from 1847 to 1976 and producing over 38,000 tons of mercury. Terlingua in Texas ran from 1900 to 1946, supplying mercury for explosives during both World Wars. By the 1970s, every major mercury mine in America had closed, not because the ore ran out, but because we finally understood what mercury does to human bodies and ecosystems. Mercury production begins underground with cinnabar, a bright scarlet mineral that's actually mercury sulfide. The chemical formula is HGS, 86.2% mercury by weight, making it the richest mercury ore in existence. Cinnabar forms in hydrothermal veins, where hot underground water deposits mercury over millions of years. Miners recognize cinnabar instantly by its distinctive red color, soft texture, and the fact that it's surprisingly heavy for a rock. A handful of cinnabar weighs almost twice as much as the same volume of granite. Mining operations followed these cinnabar veins deep into mountains. Workers descended vertical shafts on rope ladders, sometimes reaching depths of 800 feet or more. They drilled horizontal tunnels called drifts, following the red ore wherever it led. The work was brutal. Dark, humid tunnels where miners swung pickaxes by candlelight for 10-hour shifts, loading ore into wheelbarrows and hauling it to bucket hoists at the shaft bottom. The ore quality varied wildly. High-grade cinnabar contained 10 to 20% mercury, appearing as solid red masses. Medium-grade ore mixed cinnabar with quartz, showing red streaks throughout. Low-grade ore held just 1 or 2% mercury, barely visible as tiny red specks, and miners sent only the richest material to processing facilities. Processing began at crushing plants where jaw crushers broke rocks into gravel. Workers fed ore into steel jaws that opened and closed repeatedly, each cycle reducing the size. Stamp mills with heavy iron hammers then pulverized the gravel into powder, fine enough to pass through window screen. This grinding was necessary because mercury extraction works best when ore particles measure less than 1/4 inch across. The powdered ore moved to roasting furnaces, and this is where cinnabar became mercury. Roasting is simply heating the ore hot enough to break the chemical bonds holding mercury to sulfur. The reaction requires temperatures above 660 degrees Fahrenheit, the point where cinnabar decomposes into mercury vapor and sulfur dioxide gas. American facilities use two types of furnaces: direct flame furnaces, where fire touched the ore, and retorts where ore heated in sealed iron vessels. Both methods worked, but retorts produced cleaner mercury with fewer impurities. Direct flame furnaces were massive brick structures, often 30 feet long and 8 feet wide. Workers loaded ore through top doors, spreading it across a grate above the firebox. Wood or coal fires heated the ore to 750 degrees Fahrenheit. As the ore roasted for 8 to 12 hours, mercury vapor rose through the ore bed and flowed into the condensing system. Retort furnaces offered more control. Each retort was a sealed cast iron cylinder, loaded with ore and bolted shut, sitting in a brick furnace with fire surrounding it. The sealed design produced purer mercury with less contamination. Operators aimed for exactly 700 degrees Fahrenheit inside the retorts, hot enough to vaporize mercury, but cool enough to avoid cracking the iron vessels. Mercury vapor leaving the furnaces was invisible, toxic, and over 600 degrees hot. The vapor flowed through brick-lined flues toward condensing chambers, cooling gradually as it traveled. Some facilities used flues over 100 feet long to maximize cooling time. Workers built these flues with downward slopes so liquid mercury could flow by gravity once it condensed. Condensing chambers captured mercury as it cooled below 674 degrees Fahrenheit, its boiling point. The simplest design was a large brick room where vapor entered hot and left cool, with liquid mercury dripping into collection troughs. Better facilities used water-cooled pipes where mercury condensed instantly into droplets that ran down to collection vessels. The non-condensable sulfur dioxide gas vented through tall smokestacks. The liquid mercury wasn't pure yet. It carried impurities, dust particles, and traces of other metals from the furnaces. This crude mercury appeared dull gray instead of shiny silver, with purities around 98%. For gold processing, this worked fine, but pharmaceutical applications demanded higher purity through distillation. Mercury purification used distillation, the same principle as making whiskey, but with metal instead of alcohol. Workers poured crude mercury into a large iron still with a heating coil underneath. As the still heated to 700 degrees Fahrenheit, pure mercury boiled first because impurities raised the boiling point. The mercury vapor rose through a vertical pipe into a water-cooled condenser, where it turned back to liquid and dripped into collection flasks. The impurities remained behind in the still as a toxic sludge containing lead, zinc, and arsenic compounds. Facilities producing pharmaceutical-grade mercury ran distillation 3 times, creating triple-distilled mercury. Each distillation removed more contamination until the mercury reached 99.99% purity, appearing as a perfect mirror-bright liquid. Medical supply companies paid premium prices for this ultra-pure mercury used in vaccines and instruments. The entire triple distillation process took about 12 hours per batch. Testing mercury purity used several methods performed right at the facility. Pure mercury forms a perfect sphere when dropped on a clean surface, while impure mercury leaves a trail. Chemical tests used nitric acid and reagents that precipitated impurities as colored solids. The most accurate method measured electrical resistance because pure mercury conducts electricity better than contaminated mercury. Finished mercury moved to packaging, where workers filled standardized iron flasks. Each flask held exactly 76 pounds of mercury, a standard established centuries ago in Spain. Workers placed empty flasks on scales, filled them through a small top opening, then sealed with an iron plug and hammer. The outside got stamped with producer name, batch number, and purity grade. Filling flasks required care because mercury's extreme density made handling difficult. 76 pounds of mercury occupies less volume than a 2-liter bottle, making flasks deceptively heavy. Workers used long-handled ladles to transfer mercury from storage vats to flasks without spilling. Even small spills shattered into hundreds of tiny beads that rolled into every crack, requiring zinc powder treatment to form a collectible amalgam. Quality control happened at every stage. Inspectors pulled random samples from each batch and ran full purity tests. They checked flask weights to ensure exactly 76 pounds and examined seals to prevent leaks during transport. Rejected material went back for reprocessing, and nothing shipped until inspectors approved it. Mercury production served multiple industries. Gold and silver mining consumed the most mercury for extracting precious metals from ore. Chemical plants needed it for chlorine production. Paint companies used mercury compounds as preservatives, and medical suppliers wanted ultra-pure mercury for thermometers and vaccines. Military contractors bought huge quantities during both world wars for making fulminated mercury explosive detonators. At its peak during World War II, Texas mercury mines operated around the clock. The Chisos Mining Company employed over 2,000 workers, running multiple furnaces simultaneously. Production in 1943 exceeded 15,000 flasks, each representing 76 pounds of mercury from hundreds of pounds of ore. Rail cars left weekly carrying flasks to munitions factories, as the government classified mercury as a strategic war material. But mercury's utility came with terrible costs. Workers absorbed mercury vapor daily, developing tremors, memory loss, and mental breakdown. The phrase, "mad as a hatter," came from hat makers who used mercury and slowly went insane. Mining communities showed elevated rates of birth defects and neurological disorders, while red cinnabar waste leached mercury into streams, contaminating fish for miles. By the 1970s, evidence became overwhelming, and mercury production collapsed. California closed New Almaden in 1976 after 129 years. Nevada and Texas facilities shut down around the same time. Today, the old mine sites are toxic cleanup zones with warning signs, fences, and ongoing environmental remediation. Modern America imports the small amounts of mercury still needed for industrial applications, mostly from recycling old equipment. The days of roasting cinnabar in massive furnaces are over. The process worked brilliantly as chemistry. Heat red ore to 700 degrees, condense the vapor, purify through distillation, package in iron flasks. But the human and environmental costs were too high. Mercury mining and processing poisoned workers, contaminated ecosystems, and left a toxic legacy that will persist for centuries. From red cinnabar ore to liquid silver metal. From underground shafts to roasting furnaces to condensing chambers. From crude mercury to triple-distilled purity to 76-pound iron flasks. This was mercury production in America, a process that powered industries for over a century before we understood the price we were paying. Thanks for watching. Hit that like button and subscribe for more stories about the industrial processes that built and sometimes poisoned America. See you next time.
Glass. It's in your windows, your phone, that beer bottle in your hand. But have you ever wondered how something so fragile starts as nothing more than sand? Today, we're going inside one of the most incredible manufacturing processes on Earth, where temperatures hotter than lava turn ordinary sand into the crystal-clear material that shapes our modern world. The story goes back over 4,000 years. Ancient Mesopotamians stumbled onto something amazing when they heated sand with certain minerals and got a transparent solid. But it was the Romans around 50 BC who really cracked the code with glassblowing. Then in 1608, English glassmaker George Ravenscroft changed everything by adding lead oxide to the mix, creating what we now call crystal glass. Today, the global glass industry produces over 130 million tons every single year, worth more than $160 billion. From smartphone screens to skyscraper windows, this ancient craft became absolutely essential to modern life. Let's head inside a modern glass factory and see how sand becomes glass. It starts in the batch house where automated weighing systems measure each ingredient with precision down to 0.01% accuracy. The main ingredient is silica sand, about 70% of the recipe. Workers add 14% soda ash to drop the melting point, plus 10% limestone for stability. But here's the clever part. Most factories add up to 30% recycled glass to the batch. It melts at lower temperatures, cutting energy costs by 40%. Once precisely weighed, everything dumps into a specialized ribbon blender that ensures every particle is evenly distributed. Then it travels along sealed conveyor systems to the furnace. And this is where it gets intense. The furnace is an absolute beast, stretching over 120 feet long, 40 feet wide, and standing 3 stories tall. Inside, natural gas burners fire continuously at 2,800 degrees Fahrenheit, hot enough to melt steel. The flames switch sides every 20 minutes in what's called regenerative firing, where exhaust heat preheats incoming air, boosting efficiency up to 50%. Raw batch pours steadily in at 15 tons per hour. Over the next 16 to 24 hours, it slowly dissolves into molten glass. Workers monitor everything from a control room with over 50 thermocouples throughout the bath. Even a 10-degree deviation can ruin the entire batch. The molten glass gradually flows toward the conditioning zone, where temperature drops to exactly 2,400 degrees Fahrenheit, achieving perfect homogeneity. From here, different products take different paths. Let's follow flat glass first. For windows and car glass, the molten material feeds into a float bath, one of the most brilliant innovations of the 20th century. British engineer Sir Alistair Pilkington spent 7 years perfecting this process before its debut in 1959. And here's the genius behind it. Molten glass pours continuously onto a bath of molten tin, kept at exactly 1,050 degrees Fahrenheit. Glass naturally floats on tin because its density is only 2.5 grams per cubic centimeter, compared to tin's 7.3. As it spreads across the perfectly flat liquid metal surface, gravity and surface tension create glass with both surfaces perfectly smooth and parallel. The float bath stretches for nearly 200 feet. Modern lines control thickness by pulling at specific speeds. Pull faster, you get thinner glass down to 2 millimeters. Pull slower, you can create glass up to 25 millimeters thick. By the exit end, the glass is cooled to around 1,000 degrees and solidified enough to lift off without marking the surface. From the float bath, the ribbon enters the annealing layer, a temperature-controlled tunnel over 500 feet long. If you let glass cool naturally, thermal gradients would create internal stresses, making it weak and prone to spontaneous breakage. Instead, the layer cools it gradually over 2 to 4 hours. At the exit, automated cutting systems use diamond-tipped wheels to score the ribbon into massive sheets, often 10 feet by 12 feet or larger. But bottles and jars follow a completely different process. This is where the IS machine comes in, standing for individual section machine. Invented in 1925, it's still the backbone of container glass production worldwide. Molten glass flows into a feeder bowl where rotating orifice rings cut the stream into precise portions called gobs. Each gob is sheared by pneumatic scissors with split-second timing, weights controlled to within 1 gram. A typical line has 10 or 12 individual sections, each making up to 4 containers simultaneously. Here's where it gets wild. In the blank mold, a metal plunger pushes down while compressed air at 40 psi blows up from below, forcing glass against the mold walls. This creates a parison, basically a thick-walled preform with the bottle's neck already shaped. Takes just 2 to 3 seconds. Then mechanical neck ring holders grip the parison, flip it upside down, and swing it to the blow mold in less than 1 second. Compressed air at 25 psi blasts through the neck, inflating it against the cooled mold walls. From molten gob to finished bottle in 8 to 12 seconds. A modern IS machine can produce up to 600 bottles per minute. Fresh bottles travel through an annealing layer for 30 to 45 minutes, cooling gradually. Then, every single bottle faces automated inspection. High-speed cameras check for cracks and defects. Infrared sensors detect stress patterns. Bottles must withstand at least 90 pounds per square inch internal pressure. Any failures get crushed and recycled back to the batch house. For specialty items like wine glasses, skilled craftsmen still use traditional glass blowing at glory holes, small openings into reheating furnaces. They gather molten glass on a blowpipe and shape it with hand tools. A master glass blower can create a wine glass in 5 to 7 minutes. Now let's talk about safety glass. Laminated safety glass in your car windshield starts with 2 sheets of float glass with a layer of polyvinyl butyryl plastic between them. The sandwich goes through rollers at 190 degrees, then enters an autoclave at 280 degrees and 175 psi for 90 minutes. This fuses everything permanently. The result? Glass that holds together when shattered. In an accident, broken pieces stick to the plastic instead of flying around the cabin. That's why windshields spiderweb instead of exploding. Tempered glass for side windows takes a different approach. Regular glass heats to 1200 degrees, then high-pressure air nozzles blast it from above and below. Surfaces cool rapidly while the interior stays hot, creating compression on surfaces and tension in the core. This makes it 4 to 5 times stronger than regular glass. When it breaks, it shatters into thousands of small cubes with dull edges instead of dangerous shards. Here's something mind-blowing. Gorilla Glass and other chemically strengthened glasses used in smartphones go through an ion exchange process. The glass is submerged in molten potassium salt at 750 degrees for 8 to 16 hours. Potassium ions migrate into the surface, replacing smaller sodium ions. Since potassium ions are 40% larger, they create a compression layer, making the glass incredibly scratch and impact resistant. Quality control combines automated systems with human expertise. For flat glass, laser scanners detect defects as small as 0.1 millimeters. Random samples undergo destructive testing. Chemical composition gets verified using X-ray fluorescence spectrometry. Everything must meet strict safety standards. The environmental impact has improved dramatically. Modern regenerative furnaces are 30 to 35% more energy efficient than those from the 1980s. And here's the crazy part. Glass is infinitely recyclable without quality loss. That beer bottle you recycle can become a new bottle, a window, or fiber insulation. Recycled glass melts at lower temperatures, reducing energy consumption by 40%. Some plants now run on 90 to 100% recycled glass. After manufacturing, flat glass often receives low-E coatings that reflect infrared heat while transmitting visible light, cutting heating and cooling costs by 30%. Container glass exits production lines at up to 1,000 bottles per minute, packed into boxes and stacked on pallets by robotic systems. The glass industry continues pushing boundaries. Researchers are developing ultra-thin flexible glass, less than 0.1 millimeters thick for foldable smartphones and rollable displays. New formulations create transparent materials strong enough for military applications while remaining optically clear. From ancient Mesopotamian workshops to cutting-edge research labs, glass has traveled an incredible journey. But at its core, the principle remains unchanged. Heat sand hot enough, add the right ingredients, and you create one of humanity's most versatile and enduring materials. So next time you look through a window, drink from a glass, or tap your phone screen, take a moment to appreciate the 4,000-year-old craft and modern precision engineering that made it possible. From sand to something extraordinary. Thanks for watching. Hit that like button and subscribe for more fascinating looks at how everyday things are made. See you next time.
Picture this. A 22-year-old college dropout working in a woodshed behind his parents' house in Ohio. The year is 1886. He's mixing chemicals, running electrical current through molten compounds, trying to solve a problem that's stumped scientists for decades. His name is Charles Martin Hall, and in 8 months, he's about to make aluminum cheaper than silver, revolutionize manufacturing, and create an industry worth billions. But here's the crazy part. Aluminum was once more valuable than gold. The top of the Washington Monument, finished in 1884, is capped with aluminum because it was the most precious metal available. Napoleon III served his most honored guests on aluminum plates, while everyone else used gold. Extracting aluminum from ore was so expensive that it cost $300 per pound, roughly $15,000 today. Today, we're going inside Alcoa's Massena operations in upstate New York, one of America's oldest continuously operating aluminum smelters. This facility has been transforming electricity into metal since 1903. This is the story of how a college student's woodshed experiment became the massive industrial process that changed the world. Let's start with Charles Martin Hall's breakthrough. In 1886, he discovered that dissolving aluminum oxide in molten cryolite, then running electrical current through it, causes pure aluminum to separate and sink to the bottom. The process seems simple now, but it took years of failed experiments, burnt equipment, and skeptical professors telling him it couldn't be done. Here's what makes the story even more remarkable. On the exact same day, Hall succeeded in Ohio. A French chemist named Paul Héroult independently discovered the identical process in Paris. Neither knew about the other. Both were 22 years old. Both filed patents within months. The coincidence is so extraordinary that today we call it the Hall-Héroult process, crediting both men equally. Hall's discovery dropped aluminum prices from $300 per pound to just 50 cents within a decade. But turning a woodshed experiment into industrial production required enormous amounts of electricity. And that's where Massena, New York, enters the story. Massena sits on the St. Lawrence River, one of North America's most powerful waterways. In the early 1900s, entrepreneurs recognized that the river's massive flow could generate huge amounts of hydroelectric power, perfect for aluminum smelting, which consumes staggering quantities of electricity. The Pittsburgh Reduction Company, which later became Alcoa, built their Massena smelter in 1903 specifically to access this cheap hydropower. The location was strategic. Close to Canadian power sources, near shipping routes, and positioned where electricity costs made aluminum production economically viable. Today, the Massena Operations Complex sprawls across hundreds of acres along the river. The facility doesn't mine aluminum ore here. Instead, aluminum oxide, also called alumina, arrives by rail from processing plants in the southern United States and abroad. This white powder is the feedstock that becomes aluminum. The transformation happens in massive buildings called pot lines. These aren't your typical factory floors. We're talking structures several football fields long, filled with hundreds of electrolytic cells arranged in series, each one a precisely controlled chemical reactor operating at extreme temperatures. Each cell, called a pot, is a giant steel shell lined with carbon, roughly 20 feet long. Inside, molten cryolite mixed with alumina sits at 1,760 degrees Fahrenheit. Massive carbon anodes hang down into the molten mixture from above. These anodes, some weighing over a ton each, conduct electricity into the bath. The electrical current flowing through the molten cryolite causes a chemical reaction. Aluminum oxide splits apart. Pure aluminum collects at the bottom as liquid metal. Oxygen combines with the carbon anodes, slowly consuming them and releasing carbon dioxide. The amount of electricity involved is staggering. A single pot line might draw power equivalent to a small city. Massena's smelter consumes roughly 400 megawatts at full capacity. That's enough to power over 300,000 homes. The electricity cost alone represents 40% of aluminum's production cost. This is why aluminum smelters cluster near cheap power sources. Massena benefits from hydroelectric rates that make production economically viable. Without that affordable electricity, the facility couldn't compete with smelters in places like Iceland or the Middle East, where energy is even cheaper. Inside the pot lines, the process runs continuously, 24 hours a day, 7 days a week. You can't just shut down a pot. The molten bath must stay liquid. If it solidifies, the entire cell is destroyed and must be completely rebuilt, a process costing hundreds of thousands of dollars and taking weeks. Workers in protective gear monitor the pots constantly using computerized control systems. Sensors track temperature, electrical resistance, and chemical composition. Automated systems add fresh alumina every few minutes, maintaining the perfect ratio for efficient aluminum production. Every day or two, workers tap each pot to remove the accumulated aluminum. A specialized machine pierces the carbon crust floating on top of the bath, inserts a vacuum tube, and siphons out molten aluminum at over 1,800 degrees Fahrenheit. The glowing metal flows through heated channels into crucibles, large containers that hold several tons. Here's something most people don't realize. It takes 4 to 5 pounds of aluminum oxide to produce 1 pound of aluminum. The oxygen doesn't vanish. It combines with the carbon anodes, which slowly burn away and must be replaced every few weeks. A single pot line can consume hundreds of carbon anodes per year. The molten aluminum from the pots still contains impurities. It goes to the casthouse, where workers further refine and alloy the metal. Furnaces reheat the aluminum, allowing dross and impurities to float to the surface where they're skimmed off. Alloying elements like copper, magnesium, or silicon get added depending on the final product specifications. Then comes casting. Massena produces several forms. Some aluminum gets cast into massive ingots weighing over 20 tons, destined for rolling mills that will flatten them into sheet metal for aircraft, cars, or beverage cans. Other aluminum pours into smaller billets for extrusion into shapes like window frames or structural components. The most common product is the standard 22-pound ingot. Thousands stack in the yard, ready for shipment to manufacturers across North America. Quality control is intense. Samples from every batch undergo chemical analysis and physical testing. Aluminum destined for aerospace applications must meet extraordinary purity standards. Even tiny amounts of contaminants can compromise the metal's strength or corrosion resistance. Alcoa Massena has modernized dramatically over its 100-plus-year history. Today's pots produce 3 times more aluminum while using less electricity per pound than 80s-era cells. Environmental controls now capture emissions before they reach the atmosphere, meeting strict EPA standards. The workforce has evolved too. Where the facility once employed thousands doing manual labor, today several hundred skilled workers operate largely automated systems. Computer operators monitor dozens of pots from control rooms. Specialized technicians maintain complex equipment. Engineers continuously optimize the process for maximum efficiency. Massena's strategic importance became clear during World War II, when aluminum demand exploded for aircraft production. The facility ran at maximum capacity, producing metal for B-17 bombers, P-51 fighters, and countless other military applications. Aluminum's lightweight and strength made it irreplaceable for aviation. That wartime boom established aluminum as a fundamental industrial material. Today, global aluminum production exceeds 65 million tons annually. The United States produces about 1 million tons per year, with Massena contributing a significant portion. But the industry faces challenges: rising electricity costs, competition from cheaper foreign smelters, and environmental concerns about carbon emissions have forced many older U.S. smelters to close. Massena survives because of hydroelectric power access, skilled workforce, and Alcoa's commitment to U.S. production. The future of Massena and American aluminum production depends on innovation. Companies are developing new smelting technologies that reduce electricity consumption and eliminate carbon emissions. Using inert anodes instead of carbon could revolutionize the industry by producing pure oxygen as a byproduct instead of carbon dioxide. Recycling also plays a growing role. Aluminum is infinitely recyclable without quality loss. Melting scrap aluminum requires only 5% of the energy needed to produce new aluminum from ore. As recycling rates increase, primary smelters like Massena must adapt by focusing on high-value applications where recycled metal can't meet specifications. From Charles Martin Hall's woodshed to Massena's massive pot lines, the aluminum industry has transformed civilization. The metal once more precious than gold now shapes everything from smartphones to skyscrapers, from aircraft to automobiles. Next time you crack open an aluminum can or board an airplane, remember, that metal was once impossibly rare. A young inventor's curiosity and persistence made it abundant. And facilities like Alcoa Massena continue that tradition, transforming electricity and chemistry into the lightweight metal that defines modern life. From woodshed breakthrough to industrial powerhouse, from precious metal to everyday material, this is Alcoa Massena. Thanks for watching. Hit that like button and subscribe for more incredible stories about the facilities that built America. See you next time.